Okay, here's a fun little program using MATLAB that kind of helps you to understand what's going on in a PID controller. So first thing you want to do is bring up MATLAB, and then let's click on New and create a script. All right, so we've got a script here, and put a little % there for a comment sign, and then let's see, we'll call this guy PID example. All right. So, first thing I usually do is clear all my memory variables, clear the command line, and then let's set up a transfer function. How about we'll just put a 1 in the numerator, and then in the denominator we will have what, maybe a 1, 3, 1. Okay, so what that basically is s squared plus 3s plus 1. Okay. Then I want to set up my plant, and let's say the plant is a transfer function. Well, it is a transfer function with this numerator and this denominator. Right? And then let's take a feedback transfer function of 1. We'll just keep it real simple. You can go back and modify these guys later. Okay. Now, what I'm going to do here is I am going to set up a PID controller. All right. So, or actually, let's do something first. Let's create another guy. Let's call M, and we'll say open loop. So actually, yeah, M open loop. And what do we do? That let's say that guy is equal to, no, actually, let's just do M. And we'll call that guy, let's see, we'll say feed back, and it'll be the plant, and it'll be H. All right. Now, you may not have seen the feedback function, but basically what that does is it takes this as your forward path transfer function, and H as your feedback, and it does G over 1 plus GH. All right, so this would kind of be your closed loop transfer function, and let's do no controller. All right, so that's M no controller. All right, and then let's just do a step response of that guy. Step M no controller. Okay. And actually, I don't like that. Let's just call this guy M. Yeah. Okay, well, right there, I've just created a transfer function, forward path, the feedback, and then I'm going to create G over 1 plus GH, call it M, and then do a step on that. Okay, so let's run that guy. Oh, cancel. Let's see, I need to save this guy here. So let's go ahead and, actually, can I just run it? Oh, it wants me to save it. All right, that's fine. I'll save it. Okay, so if I run this, I should get a plot. Okay. And let's see, is the plot coming up? And there is my plot. Okay, so I'm applying a step function, and I kind of get a response that, looks like a smoothed out step function. So the system's responding to it. I'm putting a unit step of 1 in, but my system is going asymptotic to 0.5, so I have some steady state error. But look down at the time base right here. It's taking about 5 seconds before it finally starts approaching its steady state value, so it's a relatively long time to converge. Let's do some things here. After I do this step, let's do a grid on. Okay, see what that does. Okay, puts a grid there, so you can kind of, see 5. All right, let's see. At that point, what I want to do is I want to create some a different block of code. Notice the double print or the double % kind of sets up another separate block of code. Let's set some PID variables. KP equal to 1, KI equal to 0, and KD equal to 0. Okay. Now at this point I'm going to create a controller, GC. And what you want to do there is you want to use the PID function, and you pass it K, P, KI, and KD. But when you look at this, what are KI and KD? They're both 0. So I basically have a PID controller that's going to amplify by 1, which is basically nothing. All right. So if I do that, then what I'm going to do is create another closed loop transfer function. I'm going to call this MC. And that's going to be my closed loop transfer function with control. And again, that'll be feedback. Okay. And now my forward path is the controller times my plant, and my feedback path is H. So I'm getting two transfer functions, m up here, which is just your usual g over 1 plus gh, and now mc, which is g over 1 plus gh, but now g as a controller in the forward path. But of course now the controller is a PID with just a p of amp gain 1, which is basically just a short circuit. Right? So let's run that guy, and after we do that, let's do the same thing here. Let's do a step of MC. So now I should get two plots. I should get the step response of my system without the controller and my step response of the system with the controller. But because the controller is just a P controller of gain 1, then they should be the same thing. All right, let's run them. And there you go. Okay. All right, didn't do me a grid. Let's put a grid down here and see what happens. Try running that guy again. Okay, there you go. So I've got one plot. Really, there's two plots there. Now what you want to do is try to get understand the effect of changing PI and D. Because what we did here is we did two-step responses, but they're the identical transfer functions. Now I'm going to change my PID controller. So I'm going to highlight the KP variable, which is 1. And then I'm going to hover over that guy and right-click. And I'm going to choose increment value and run section. And that run section, well, that's the reason I put those two percent signs in here. So I've got this section highlighted with those 2 percent signs, and now I've got this little box where I can increment the value of KP and run it. So right now KP is 1. If I hit the plus sign, it's going to go to 2, and it's going to rerun the script here. So let me hit the plus sign, and let's see what happens. Right. Run it again. Okay, now what's happened? Let's see. Oh, I don't have the hold on. That's what I want. Yeah, let's go back up to here. And instead of changing the grid, let's put this to hold. All right. And then we'll, let me actually go back here and do this again. All right, put that at 1. And let's see. File, let's go ahead and save all this. Let's kill the plot so it'll come back up. And let's run the entire thing. Okay, so there is my step response. Now let's play that same game. Let's go to KP, right click, increment value and run section, and now let's increment it to 2 and rerun it. And there you go. That's the picture I'm looking for. Now up above here I've got just a controller with the, or I've got a plant with a feedback, and that's the green plot you see over here. Goes asymptotic to 0.5. It takes about 5 seconds to get there. But the red plot is the lower code over here where I've actually put a controller in. And all I did was put a P controller with 2. And we kind of showed in class that that P controller basically just makes the system do what it's going to do but faster. And it could change the steady state error here. Now you can come over here and right click on this guy and look at steady state. And then these dots here say, well, as t goes to infinity, the green plot's going to go to 0.5. The red plot's going to go to 0.667. Well, I want it to go to 1. Okay, so I do have some steady state error. Well, let's keep increasing KP and see what happens. Oh, now, hey, yeah, look, I'm getting actually in the steady state closer to 1. This is 7.5, this is 6.67, and this is 0.5. But now I'm getting a little bit of an overshoot there for my steady state. Let's increase it some more. Oh, I'm actually getting closer to 1.0 with more overshoot. Keep increasing it, keep increasing it. You see what's going on? We're getting closer to 1.0, but we're also adding overshoot in there. Every time I run that, yeah. So every time I increment k sub p, and you notice down here that k sub p is changing, and it's changing by 1 every time. It increments it and runs it. So yeah, I'm basically getting a much faster response because the green plot over here was my initial system. It took 5 seconds to basically stabilize. And then now with my P controller in there, it's pretty much hitting its final value at like 1/3 of a second. Problem is I got a little bit of overshoot. Okay, now I'm going to close this plot and rerun it so we can get a fresh plot. Okay, so currently the blue plot is what we started with no control. The green plot is a controller with it's a P controller with 13. Let's bump that guy up a few more times and get some overshoot. Yeah. So as I keep increasing that, notice the rise time. How quick I'm coming up to speed is getting better. It's getting smaller, so it's responding more or getting quicker. but at the expense of more overshoot. All right, so let's do a few more. Yep, there you go. We increment, and now KP is at 24. All right, I'm going to stay at KP equal to 24. Okay? So let me get a fresh plot here. And that's the effect of a P controller. Now let's go down to the D and start incrementing that guy. Well, a lot of people say we need to damp out these oscillations, but damping isn't really the correct term. Because if you remember, like a periodic pulse train is a Fourier series with an infinite number of terms. Well, if you don't pass those higher terms, those terms that are up near infinity, what you're going to do is you're going to get ringing in your output. Because the really, really high frequency components are being filtered out on a perfect edge. So what we really need to do is allow high frequencies to come in here to kind of turn that oscillation into more of a square edge. And how do you put more high frequencies into your system? Well, you do that with derivative control. So over here I've got KD, and I'm going to highlight the value, and I'm going to start incrementing KD. Now look what happens to the response. Hey, we're starting to damp out our oscillate. Now, don't say damp. Damp is the wrong word. We're starting to add bandwidth to our system, which allows higher harmonics to come in, which allows me to get edges in our signals. Discontinuity and edges are really high frequencies. So we're allowing more high frequencies to come in, and look at the response. Yeah, we're actually going up there and boom, making a hard right turn and kind of stabilizing, as opposed to that ringing effect, which means you're filtering out the really high harmonics. Okay, so I'm going to close this one and get me a fresh plot again with run. And now what we've got is we had a system that took about 5 seconds to stabilize, and then we put a P controller with coefficient 24, a D controller with derivative controller with 8, and now we've converted that blue one into a green one. That's a pretty darn good response. But now there's another issue here. Steady state. The blue controller went to 0.5 when our input said go to 1 because it was a unit step. Well, the green response went to 0.96, which is pretty close to 1. But we're not going to be able to get to 1 unless we put some integration in here. So let's go over to this guy and highlight our KI. And then what I'll do is I'm just going to increment that guy 1 and watch the green plot. What's happened there? Okay, it increased a little bit. And notice the red plot now has a final value of 1. The green plot has 9.6. So by me putting that integrator in there, I zeroed out the steady state. And I put a 1 in there, and I get a 1 output, and I got a really nice quick response. I have minimal overshoot, and here is my PID controller. Now I'm using the PID function to get G sub C, and then if I go over to my command window and I type G sub C, then there's the transfer function, which we talked about in class. There's your P, there's your I, and there's your D, and then there are your values. And you basically tuned a PID loop. Okay, now here's an exercise left for you guys to try. Let's go up and change our plant. Okay, let's change our plant to a third order system. So now I've got some physical entity that I'm trying to control that's a third order system, S cubed plus S squared plus 3S plus 1. Let's run it and see how our PID controller works with that guy. Okay, let's close the window. Ouch! Well, for a third order system, what happened? With that PID controller, it blew up. So, exercise left to the reader. Figure out how to tune that third order system. All right, I'm going to stop there. I've talked way too long. See you later.